All right, everybody. So, topics in this video: higher order derivatives, velocity, and acceleration, which at least at the time I'm making this is for some stuff I'm going to put on WebAssign. But these are very generic topics for anybody who takes Calculus 1. You'll see problems just like the ones you're seeing here in this video. But anyway, so let's start with higher order derivatives. To give an example of that, it might be that you have some function, whatever it is, it might be one like this, it might be one like that, and we might have the task of finding the second derivative or the third derivative or whatever. If you can find one derivative, you can find all the ones after that if you just repeat the process. So when we find the second derivative, for example, the rules don't change. You use the same rules that we've already learned. Okay? So, all right, for example, let's take this one. If I'm going to find the second derivative of this function, I've got to start by finding the first derivative. So, okay, we'll go and we'll do this first. Find f prime of x. And what do the rules say we do for that? This constant right there, 7, we bring that down, and we multiply it times the derivative of x to the 3 over 2 power, which is 3 over 2 times x. Well, what do I do next? I take 1 away from this, so that would be 1 over 2. Okay, so the first derivative would be 21 over 2, right? Times x to the 1/2 power. All right, so then I've got the first one. The second derivative is just defined to be the derivative of the first one. So I just repeat the process, right? Like I told you, it doesn't change the rules. The rules are going to be the same. So I'd say, okay, what's to find f double prime? What's the derivative of this? 21 over 2 times x to the 1/2 power. Well, again, that's 21 over 2. That being a constant where it is right there, we carry it down and we multiply it times the derivative of x to the 1/2 power, which would be 1/2 x to the negative 1/2 power. Okay, so and then there's your second derivative, where who knows, maybe you could simplify that, maybe you can't. This time we can do some simplifying, but you see how we got there regardless of how we simplify it. Okay, so in terms of simplifying it, it's the constant right here. What's that number? 21 over 4. All right. And then the variable x to the minus 1/2, I'll carry that over. And we'll probably write this with a positive exponent on one hand and root notation on the other hand. So let's say, let's give our final answer like this, 21 over 4. And then down here is going to be x to the 1/2 power, which would otherwise be like so. All right. And then there's your second derivative. Okay, so same rules, but we'll repeat as much as we have to find a higher order derivative, the second or third or fourth or so on. Okay, so let's take one more example like that. So let's see, let's do this one with the product rule right here. Yeah, x times sine x. It says find f double prime of that. And I say with the product rule, I mean, I hope that's apparent that this original function, if I was going to find the first and then the second derivative, I would have to use the product rule to get that started. Okay? So, well, let's see. F prime. To find the first derivative in our first step. Okay, with the product rule, that's going to be f prime g plus g prime, derivative of sine's cosine, times f. All right, so the derivative of x is 1, but then times sine x, plus the derivative of sine x is cosine x, and then times x. So that's the way that we've been using the product rule. All right, let's go ahead and simplify this a little bit. Like I wrote the 1 right there just to make it obvious to how I was using the product rule. So we'll just say sine x, and over here I think it's customary to put the x there in front as a coefficient of cosine x. So we'll say, let's go ahead and write this x times cosine x. Okay, now we'll repeat, right? If it is the case that we want the second derivative. So, okay, f double prime is the derivative of f prime. F double prime is the derivative of sine x plus x times cosine x. Well, so how would we do that? Remember, the rules don't change when we do this. So it would be the derivative of sine x plus the derivative of x cosine x. And to find the derivative of sine x, well, that's just going to be cosine. And I carry down that plus because that's what you do when you take derivatives. And then I find the derivative of x times cosine x, but I have to use the product rule for that. Okay, so right here is the product rule derivative of x times cosine x, which is again going to be the derivative of x times cosine x plus the derivative of cosine x, which is minus sine x times x, right? Okay, so well, let's do whatever simplifying we can. This will be our final answer. I'll get cosine x plus cosine. I'll get 2 cosine x. Okay, because there's 2 of those. They're like terms. And then here I'm like adding what turns out to be a negative. And say I move this x, that number, as the coefficient of sine. I'm going to get minus x sine x. Okay. And there's your second derivative. All right, so the rules don't change, though. Most important take-home message from this, the rules don't change. Let's look at something to give us a purpose for finding higher order derivatives. So that will bring me to telling you a little bit about position, velocity, and acceleration. And in order to do that, I need you to like think of a scenario. So this requires a little bit of your imagination, all right? So suppose an object is moving along the number line, like maybe back and forth along the number line. And suppose I even give you a formula, a function, that tracks the location of the object as it moves around. So like, just suppose, just for the sake of example, right now, I tell you s of t is t squared. Now, when we use notation like this, s typically means the position of an object, and t is the time that it's at that position. And you can do the measurements however you want, but in this one I said, let's suppose the position is in feet and time is in seconds or something like that. Now, all right, I want you to have a little insight into thinking what that is going to be like. Okay, so what would it be like, in other words, if an object was moving according to that equation or that function right there? Will it be something like this? Now, again, I said there's an object moving on the number line. Okay, so let's say here's the number line right here. And let's say that we've marked it off in feet. Like, so there's 0 feet, 1 feet, 2 feet, 3 feet, 4 feet, 5 feet, 6, 7, 8, 9, 10. You get the idea. So say we've got this straight line. It could be a track or a road or whatever you want. And we just marked it off every foot. Well, if you were moving according to this, you would be here when t is 0. Because if I put 0 for time, 0 squared is 0 for position. And you would be here when t is 1, all right? Why is that? Why would you be at the 1 foot mark at t is equal to 1 seconds? Well, because when you put t is equal to 1 in here and you square it, you get 1. And you would be here when t is equal to 2. All right, why is that? Well, because when you put 2 for t, you square it, you get 4. So when t time is 2, s the position is 4, right? One more. You would be here when t is equal to 3. Why is that? Why at the 9-foot mark when t is 3? Well, because same reason as the others. 3 squared is 9. At the 3-second moment at that time, your position is 3 squared, which is 9. So something that would move according to this starts off kind of slow and starts speeding up, and it's going to be moving to the right. Why do I say it's going to be speeding up? Well, because in the first second, you move this far. In the second second, you moved further. And in the third second, you moved even further than that. So if you just look at the places here and the times, you're covering greater distance in equal time, therefore you're speeding up. Okay, so time for some concepts related to this. Average velocity, okay? So suppose I give you a time interval like t is 3 to 3.2 seconds. So what's the average velocity during that time interval? Very easy formula. I'll just start by writing the formula down. We take the later time and calculate the position at that time minus the earlier time and calculate the position at that earlier time. That would be like this, wouldn't it? Here's your position when t is 3.2. You know, it goes in there, 3.2 squared. And here's your position when t is 3. Goes in there. And then I divide by the difference in time. So if you look at this, this is how far you went over that much time. And this is how much time it took you to do that. What are the units here? Feet per second, feet over seconds. That's a velocity. That's a number that describes how fast something's moving. So let's do the math as far as this goes. And I'm going to get 3.2 squared minus 9. As far as that goes, that's 1.24. All right, 1.24. And what did I say that was? That's feet. From this time to that time, what this tells me is that's how far you traveled. From the time t is 3 to 3.2, in that 0.2 of a second, you moved 1.24 feet. Okay? And yes, that took 0.2 seconds. All right. So that's the numbers and then the units for each number. So we'll divide that out. I mean, it says that over this time period, you traveled 1.24 feet and it took you 0.2 seconds. But we reduce that. We divide it by 0.2 and we'll get it's about 6.2 feet per second. There's my average velocity. Okay. All right, so that's how you calculate average velocity. You have to give me a time interval, a time duration. I have to say calculate the average velocity from this time to that time. And then there's our formula for it. Okay, what about instantaneous velocity? Well, this is the velocity over a period of time, say 0.2 of a second. The instantaneous velocity is the velocity at an instant, at one single moment, such as the moment when t is 3. All right, well, the definition of instantaneous velocity is that it's just the derivative of the position function, okay? So if s of t is the position, the derivative of that would be the instantaneous velocity. Well, that's pretty easy in this case. The derivative of t squared is 2t. And at time t is equal to 3, then that will be 6. And it will have units to match that. It'll have units to match the average. 6 feet per second. Okay? All right. What's that mean? Well, at that moment, that's how fast you'll be going. That's your instantaneous velocity. Somebody might say that, well, there's a paradox here because at that moment, nothing is moving, right? Here I'm saying you're going 6 feet per second, but at that moment, nothing happens. At 2 p.m. today, everything was standing still at 2 p.m. today, for example. So what does that mean? It seems like kind of a paradox. All this means is that if time were to progress from this instant, such as there, this would be the limiting value of the average velocity. So see how if I say, well, we're going to let the thing move a little bit. We're going to let it move from t is 3 to 3.2. We're going to measure the distance over the time. Yeah, we didn't get exactly 6, but we got pretty close. If that was 3 to 3.01, this would have been a lot closer to 6. So that's what we mean by instantaneous velocity. All right, next thing. What's the instantaneous acceleration? Well, this will be v of t, all right? So I'll say v of t, the instantaneous velocity at any time, not just the time when t is equal to 3, is 2t. There's a formula where I would calculate in general the instantaneous velocity. Okay, so v of t, that's our notation we use for the instantaneous velocity. What's the instantaneous acceleration? Well, all right, so that is the derivative of the velocity. Maybe you see a pattern here. You have your position. If you take the derivative of it, you'll get your velocity. And if you take the derivative of the velocity, you get the acceleration. We might call the acceleration v prime, or we might call it a, or we might even call it s double prime, right? Because we started with the position. We took the derivative of it twice to get the acceleration, okay? All right, well, pick whatever notation you like, but it's a second derivative. Where do we start? We started by finding higher order second derivatives. Okay, so in the case of giving a position function to start with, the second derivative of it would be the acceleration. In this case, what is it? What's the derivative of 2t? It's just 2, okay? Units, what are the units of it? Well, so it's going to be feet. Whoops, okay. It's going to be feet per second squared, okay? 2 feet per second squared. What those units probably, if you've never seen units like that, probably seems a little bit strange. So let me explain it like this. So first I'll tell you that the acceleration is constant. It's not 2t, it's just 2 feet per second squared. But here's a real quick explanation on the units there. So let's say that generally, just in very rough terms, velocity measures change in position per unit of time. And acceleration measures change in velocity per unit of time. So say I took the velocity and I measured it at different times and I tried to see how it was changing. Like say when t is 0, what's the velocity? It's 0 feet per second. And when t is 1, the velocity is 2 feet per second. It has the same units. When t is 2 seconds, the velocity is 4 feet per second. And when t is 3 seconds, the velocity is 6 feet per second. Okay, so it's got the same units for each one of them. How does it look like it's changing? It looks like for every second, the velocity changes by 2 feet per second. So you know how we use the delta notation. So delta v over delta t. How does the velocity change as time changes? Well, look at my numbers. What's 6 minus 4? What's 4 minus 2? What's 2 minus 0? The velocity is definitely changing by 2 feet per second. For every, how's the time changing? 1 second. Okay? So 2 feet per second per second. We write that as 2 feet per second squared. To say the velocity changes by 2 feet per second, well, we do a little math with the units and we get second squared. That's the reason it works out that way. Okay, So let's try something a little harder than this. This was a pretty easy one as far as it goes in the big picture. All right, so let's do this one. So imagine this scenario. A lead ball is dropped from a height of 1,373 feet. And say that when objects are in free fall under only the influence of gravity, they have this predictable position function. Okay? So in the case that something is just dropped and it's just falling, then there will be its position above the ground. All right, that's what this tells you. It tells you how high above the ground the object is at any moment. Okay? All right, that's what it does. I told you that. And say that the position will be in feet above the ground and time will be measured in seconds, as I indicated. Anyway, so let's say like that's the premise of the question, all right? I have several parts of this one that I want to explore with you, all right? So first, what are V of t and S of t? Well, all right, we have to read between the lines a little bit here. In this general equation that all objects under free fall are going to obey, V0, V naught, is the object's initial velocity when it starts to move, all right? And S naught is its initial position, okay? So S of t then, with some updates to this, is going to be, well, V naught is 0. If you just release something, that moment that you let go of it, it actually hasn't started to move yet. So V naught is 0. S naught is its initial position, is 1373. So I'm going to get negative 16 t squared plus 1373. Okay? So there's my position function. This will tell me how high above the ground the object is at any moment. What's V of t? V of t is the instantaneous velocity. The velocity at any instant or any moment is the derivative of the position function. So that'll be S prime. Okay? S prime, well, that will be negative 32t. All right, so there's my position, and there's my instantaneous velocity. Okay. Next part, what's the average velocity over this time period from t is 1 second to t is 2 seconds? Well, okay, so remember our formula for that. I said calculate the position at the later time minus the position at the earlier time divided by the total difference in time, meaning the later time minus the earlier time. So that's the same formula that I used in that other example, but here it is again. All right, so here I'll do the calculations off screen. I'll tell you what I get. Make sure you get the same thing. Okay, so if you do that, you will get negative 48. And what would the units of average velocity be? That'd be feet per second. Okay. All right, so why negative? Well, okay, so here, where did I start with this? Let's see. Let me get my other piece of paper. I said the model was an object was moving along the number line. And I drew my number line like this before. If something was moving to the right, its velocity would be positive. And if it was moving to the left, its velocity would be negative. All right? Now here, this object was strictly moving to the right, so I got only a positive number for the velocity. Here, if I say something is dropped, then the way that we imagine the number line is that it's up and down, because like something that is under free fall, only under the influence of gravity, would fall in a straight line towards the ground. So the fact that this number is negative right there just means that it's falling from the perspective that we have our number line imposed on this situation, okay? But on average, over that time period, it's moving 48 feet per second. Okay, so instantaneous velocity at the time t is equal to 1. Well, you just have to remember the definition of instantaneous velocity. So, well, what was that? Instantaneous velocity, that's going to be s prime. Okay. And we worked that out already. And we got it to be negative 32t, right? Okay, yeah, we did that up here. And at the time t is equal to 1, it's going to be moving, well, whatever 32 times 1 is. Negative 32 units feet per second. Okay. All right, so this next part, we'll read it, maybe think a little bit about it before we decide how to do it. But it says, calculate the time required to hit the ground. All right, so let's think a little bit about how to use what we have to do this. I have something which tells me how high above the ground this object is at any moment. That's what S of t does. It tells me the position as far as how high off the ground it is. So I guess if you want to know the time it's going to hit the ground, then your first question to address is, when is it going to be on the ground? So when will the position be 0, right? And in that case, that's going to, what's S of t? Negative 16 t squared plus 1373. So if you can solve this, that will tell you the time that it's going to, the actual moment that it's going to hit the ground, okay? So, well, that's not too hard to solve by calculus standards. If we, say, move the 1373 over, it'll be negative. We divide by 16, which is also negative right there. We'll get the square root of 1373 over 16. Okay. Now, probably we'll be asked to round this one. So let's see, what is that? Root 1373 divided by 16 turns out to be, well, you'll have to round, like whoever's asking you to do this, you have to round however they want you to. So say it was 3 decimal places, 9.264 seconds. 9.264 seconds. That's how long it's going to take to hit the ground. It's dropped. It begins to fall. It speeds up faster and faster the longer it falls, and then it hits the ground shortly after 9 seconds of falling. Okay. All right. Maybe the calculation's not so hard, but you got to know this is where you're going to start, right? Okay, so that's the time that it hits the ground. What's the velocity on impact? Well, all right, I know the time. I want the velocity. That's this other thing, right? V of t is the instantaneous velocity. So let's say we're going to find V of, that number right there, which is going to be negative 32 times that number right there, which means it's going to be moving pretty fast when it hits the ground. 32 times 9, that's fast, but let's see. I got the number in there already, see, right there. I just do times 32. So it'll be moving almost 300 feet per second. Let's see, I'll do the same rounding. We're going to have to round this number. However we're supposed to, I'll do 3 places. It's negative, right? It's falling. Negative 296.432 feet per second. That looks messy, but, well, you see it, right? It's moving fast when it hits the ground. When t is equal to 1, it's not moving that fast. It hasn't been falling for that long, 32 feet per second. When t is 9, it's moving significantly faster. All right, that shouldn't surprise us. We know how falling objects work. So let's do one more. I think that will probably cover the topic okay. So let's do something like a variation of that last problem. Suppose a lead ball again is thrown downward. So not dropped, but actually thrown downward towards the ground. From a 420-foot building with an initial velocity of negative 28 feet per second. All right, negative meaning that it's moving downward. I throw it downward 28 feet per second. Remember this last one, we said that as it's just dropped, its initial velocity is 0, okay? But if you throw it with some force, its initial velocity is not going to be 0. Now, all right, let's start with, well, how do we, this is generic, right? Anything in free fall under only the influence of gravity is going to obey this equation just like the last problem. It's just that v naught is negative 28. That's my initial velocity at the moment it starts to move. And s naught is my initial position. So it starts off being 420 feet above the ground, moving at negative 28 feet per second, right? So if I want to find the velocity, I got to start by getting all this in order. So let me say that, all right, s of t is going to be negative 16 t squared minus 28t, okay, and then plus 420. So there's your position function. What does this do? It tells me, in this case of something in free fall, how high above the ground the object is at any time, okay? And I want the velocity. Now, you could say, well, do you want the average velocity or instantaneous? We've talked about both of them, haven't we? Average velocity, instantaneous velocity. Well, usually the convention is when we say velocity alone, we mean instantaneous, okay? So what we're looking for is s prime. Remember, the instantaneous velocity is the derivative of the position. That will be negative 32t, okay, minus 28. That's the derivative of negative 16t squared minus 28t plus 420. So there's your velocity at any time. And to find it at the moment when t is 4, you just put 4 into it, all right? So I'm looking for the instantaneous velocity at the instant when t is 4 seconds, okay? Negative 32 times 4 minus 28. So I get 156. Negative 156 what? Feet per second? Yeah, there you go. Okay. And now this. What is the velocity after falling 228 feet? Okay, well this one does take a little bit more thinking. What's the velocity after falling 228 feet? So let's think of it like this. To know the velocity at all, I have to know what time you're talking about. So when you say that it fell 228 feet, then it doesn't tell me the time. So I got to figure that out. So let's do some thinking like this. Let's say, well, I got this building and it's 420 feet. Okay? All right. And you throw the thing towards the ground from 420 feet above the ground. And then I say, okay, so it falls 220 feet. Okay? Or 228 feet. And, well, how high above the ground is it? Well, I need to do 420 minus 228 in order to figure that number out. And that turns out to be 192. So when you say the object fell 228 feet, you're telling me it's 192 feet above the ground. Why is that important? Well, because what does the position function do? Well, I told you that here's the way this is meant to be understood. This tells you the height above ground of an object in free fall. For it to have fallen 228 feet means it is 192 feet above the ground. So I need to know the time that it takes to get there. All right? That's what I got to figure out. So how about this? Let's say, given that we want the position to be 192, let's solve it at that position and find the time, because that's what we need, okay? So think about it like this. All right, so we want the time when you got that position. So here's our position function. We'll get negative 16t squared minus 28t plus 420 equals 192. Okay, and that turns out to be a quadratic equation. So say I moved the 192 over there to solve it like a quadratic, because a quadratic equation is something that everybody who gets into calculus learns how to solve at some point. Then it will be like this. We'll get 228 and 0. That's a quadratic equation when you get the 0 there. So you could factor it, I guess, if you're really up for a challenge, but why don't we just use the quadratic formula? It's an easy way to solve a quadratic equation. So you take the opposite of that number, plus or minus root, and then you square that number. But negative 28 squared is the same as 28 squared, so I'll do like that. Minus 4, negative 16, 228. All right. Over negative 32. So that when I work this out, that'll be the moment when the object's 192 feet above the ground. That'll be the moment when it has fallen 228 feet. So as far as this number goes, there's no nice way to do it. I just gotta work it out. So let's see. That number is, I could just do all this on my calculator if I wanted to, but let me just write down some of my intermediate numbers. This number is 15,376. And then that's negative 32. And then 15,376 is a perfect square. It's 124. So we're going to get 28 plus or minus 124 over negative 32. Now, obviously, there's two answers in here. 28 plus 124, 28 minus. There's two numbers. Only the positive number would make any sense for us. Of those two things right there, the plus or the minus, the one of them that ends up being positive is the minus. If you do 28 minus 124, that's a negative number. Divide by negative 32. That's a positive number. If I do that, I'll get t to be, what do I get? 28 minus 124. Okay, so that turns out to be a nice round number. It's just 3. Okay, so it will take you 3 seconds to fall 228 feet. All right. So when you do all this, what were we even trying to find? It says, what's the velocity after falling 228 feet? So at that moment, when it has fallen 228 feet, when it is 192 feet above the ground, how fast is it going? Well, there's the time. You just put the time in to the velocity, right? That's how it works. So our answer is going to be v of 3, which is negative 32 times 3 minus 28. All right, I know the time that I want the velocity at. So, okay, negative 32, 3 minus 28. So that turns out to be 124. Negative 124 units feet per second. Okay. Moving downward, because the negative says it's moving downward, and how fast? 124 feet for every second on the clock. Imagine something 1 second goes by and it moves 124 feet through space. That's pretty fast.